Can people hear me? And I have to wait that awkward amount of time for the stream to buffer and get through the chains of processes. How are we all doing? I still haven't seen a chat message to say you can hear me. Yes, yes, yes. We'll be starting soon. My laptop decided that I raised my standing desk up just before the stream, and I'm guessing something happened with the dock connector, and it just crashed. So I had to quickly get everything set up again. So hopefully I haven't forgotten anything, but I think we'll be fine. And Droppy isn't back yet, so at some point you'll have Droppy come through here with a bicycle, or awkwardly try and sneak past. I don't know how he'll try and do that. We'll see. So let me see if everything's working. Oh, I need my presenter notes. Where have they gone? Ah, over there. Right. I should maybe post this here. And yeah. Oh, it didn't post in Hamfurs. I don't know. Is anyone awake in Hamfurs at the moment? I don't know how time zones work. Cool. Hello. And I don't know how to use Twitch, but I think I've got messages turned on. So hopefully Twitch people, if there's Twitch people, can comment, ask questions. We are at 7 p.m. However, my post did say 7:01 to avoid confusion for midnight time zone people. So we do have 30 seconds to awkwardly hang out. Not that we're really running a tight ship here. This is the least prepared I've ever been for a talk. I was writing slides this morning, along with trying to get everything to build and deploy and all of that sort of stuff, and fixing up my blog post. So it'll be interesting to see how this goes. Hey Alex, good to see you. Hope your day was good. Yeah, so should we get started? I think we can. I'm just essentially wagging my tail here, excitedly. This is an exciting project for me. That's why I'm so excited about this, that I can finally close it out and work on something else, which is even more exciting. So yeah, I think we'll kick it off and see how we go. So let me work OBS. There we go. Right, so how to hack a radio, defeating Codan's anti-competition security system from 1993. I'm Michaela, pronouns she, her, VK3FUR. There's my email address there, and my Mastodon and Fedi if you want to contact me, either email, Fedi, whatever, to ask questions after the thing. Just send them through to there. I don't bite too hard. Cool. So, once I work out how to drive this, cool. And we'll do This, yes, everything is working. So, housekeeping. Make sure you know where your nearest fire exit is. It's always good practice. But this is not an important talk at all. This is a thing that I find important. It's a topic I'm interested in. But if you have friends, family, hobbies, or it looks like a nice day outside, and you feel that's more important, definitely don't don't be in this talk. Just go, do the thing. It doesn't matter. I don't care if I'm talking to nobody. Um, I want you to do the important things that are important to you. So make sure you do that. Also, given the times, please reach out to your friends and families and, you know, just tell them that you love them or, see how they're going, make sure everyone's okay. Sometimes just talking to people, just saying hi can be a really big thing for people. So if you've got a few moments now, just quick text message, maybe Codan Pagecall if you have a Codan radio. Other thing is, this is not my professional work by any means. I'm not a professional reverse engineering person. I'm also not a professional radio person. I do amateur radio, not professional radio. Professional radio was a previous job of mine. So that means like the quality of this work is terrible. As I was mentioning just before, I put these slides together about 7 hours ago. So there hasn't been a lot of polish in this, nor has there been any polish in the reverse engineering I've done and the Python code that goes into free cell call. But it also means I'm not under any sort of NDA for this work. So if you have questions or want to know anything, definitely do that. This is definitely not a tutorial. We're not going in depth, just an overview of everything so we can pull this entire story together and so you can understand what the heck I've been doing for the last 7 months. Feel free to put questions in the chat. I probably won't be able to read them while I'm doing the presentation, but at the end I'll try and answer them, or I'll try and reach out to you. Otherwise, yeah, send me an email or get me on Fiddy. Cool. The other thing is links to these slides will be available after the talk, and there is a write-up on my blog already that is already available. So if you're not the type of person that likes video content or streams and that sort of stuff, you're not missing out on anything if you go check out the blog. The code's already up on GitHub. If you just want to jump straight into that, you don't have to, tire yourself out for no good reason if this is not something you want to actually listen to. So jump into there. Won't feel offended. Make yourself at home. Yeah. And then just quickly, do you want to waste your time on this talk? So what's going to happen in this quick HF radio primer? This is so the reverse engineering folk know what the heck a radio is. What cell call and free cell call is, page call and the problem, how processors, microprocessors, CPUs work. This is so that the radio folk know what's going on, and we'll combine that together to look at emulation and reverse engineering techniques, and hopefully come up with a solution for the page call problem. So let's dive in. So HF radio, very high level. If you want to know more, just find any amateur radio person and they'll talk hours and hours and hours about this stuff. But importantly, it bounces off the ionosphere. And what that means is you can get further than line of sight with HF radio. It's very useful for when you're traveling far distances. You might not have a cell phone tower in reach, so you can use HF radio to get in contact with someone. We use that significantly on our CSR trip. where we didn't have any other sort of service to regularly check in with people. So we used HF radio. We did things like send emails, talk, that sort of stuff. No cell phone reception at all over HF radio. So what's the HF in HF radio? It's high frequency, and high frequency radio is some of the lowest frequencies that we use day to day for radio. Your phones are all on hundreds of megahertz, and your Wi-Fi, that's in gigahertz. HF is all the way down in tens of megahertz. So we regularly use 7 megahertz on our trips and 10 megahertz for APRS and stuff, but yeah, quite low compared to your day-to-day sort of stuff. But not line of sight, vast distances, very, 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 very fun, and very useful. So we use it in our car when we're traveling, as I said. That gives us some car-to-car communication if there's other travelers that we happen to be able to talk to. There's also a car to base station. In Australia, we have services like VKS 737 and other HF radio services for travelers. Also, Royal Flying Doctors service, so that can be accessed through HF radio. And it's very, very, very useful. There's no sort of you don't have to worry about intermediate sort of things like repeaters or satellites. As long as the ionosphere is playing nice, you'll be able to talk to someone. And with VKS 737, they have enough base stations around that you can usually get somewhere. But the problem is you don't want to be listening to like static all the time, right? So like, how do you organize these contacts between people? So you can do scheduled contacts. That happens on VKS 737. You can set up friends. Like Mark has been wonderful. We've set up just scheduled contacts while we're traveling with Mark, and that's been fantastic. But the other option is this thing called cell call. And what cell call is basically a way of calling another radio. You punch in a number, it will send a message to the other radio to say, hey, this other radio wants to talk to you. It's pretty basic. It's sort of just to trigger, hey, someone's trying to call you. It can be used to trigger like emergency operators. So we're talking about RFDS before. What you can do is dial a specific number, and that will patch in one of their operators to be able to answer your medical emergency or whatnot, and hopefully get it all sorted out. Otherwise, someone has to be sitting there listening constantly. So that's one of the use cases for cell call. The radio can ping back as well, so you can get an idea of what the conditions are like, if you can hear the other station, if their radio is turned on, if it's set to the right channel, that sort of stuff. And in these Codan radios, it's all built into the radio, so you don't need any sort of extra hardware. The only problem is this protocol, this cell call protocol, is specific to Codan. Other companies like Barrett have also implemented it as well, which we'll sort of get into a bit later. But there have been some amount of software made to do this like cell call thing openly as well. Very few open receivers, so free cell call is a little bit different in that it can also receive these cell calls. So how does cell call work? Not really going to dive too much into the modulation of that, but I know some people would want to know. So just quickly, it's sent over the same channel as the voice. So it's not changing channels or sending it a different way. It's the same channel that you talk, with the microphone on. It's 2 tones, so 2 FSK. That means there's one frequency for a 1, one frequency for a 0. And it's 100 baud rate. That offset between the 2 tones is 170. Blah 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 blah. The important thing is it's a very basic. FSK is very known. We have good modulators and demodulators for it. Cell core itself is terrible, though, for multiple reasons. I've been told that the 170 hertz split in the 100 baud rate causes all sorts of funky radio issues. Mark's in the channel, so you can ask Mark what it all means. I think he told me this. I don't know. The other problem is it doesn't have a whole message checksum. Everything's repeated twice, which is good, and there's parity bits on each word, which is kind of good, but you can't verify a whole message. But to be honest, it doesn't really matter for cell call. It all seems terrible, but at the end of the day, you need a high enough SNR to make a voice contact that if you can't get the cell call to work, you probably can't get the voice contact to work either. So it kind of, whatever, it doesn't matter. So what is Free Cell Core? Free Cell Core is open source software I built with the help of Mark and a ton of other people. Uses modems from Codec 2, so David Rowe, shoulder of giants here. I've done a small sliver on top. That you can have a mobile phone connect to a web app, which is running on a Raspberry Pi, and the Raspberry Pi is connected to any HF rig. As long as you can get sound and a PTT control into it, you can send and receive cell call on that rig. And it's all open source and free, and it will also receive cell calls, and you can get it to do things when you receive cell calls. Has a WebSockets API, so you can build applications onto it. But yeah, it's a nice software solution. One thing that's cool about it is we can extend it, so if we want to add other cell call protocols, or even our own, which we think are better, we can add it to it while still maintaining compatibility with the old systems. So we can expand on this if we want to. Pages. We're slowly getting to the problem. I'm sorry, it's taking a little while, but I sort of need to explain the progression here. So pages, basically like SMS messages or WhatsApp messages, Telegram messages. I don't know how are people communicating these days. Limited to 64 characters between radios, sent pretty much with the same protocol as a cell call with a few tweaks. Can be sent and received without a computer, so you can do this entirely on the radio itself. So you can just be typing in using the microphone has keypads on our 9323. You can type it all in there, hit send, and it will send it. The other radio will respond back with some beeps to say, hey, received your page, and it will alert the user at the other end that there's a message there for them to receive. The only problem is implementing this in Free Cell Core has been a bit of a problem, because although we know how to receive page call messages, there's these 2 bytes in the protocol. They're repeated twice like everything else. These 2 bytes, some sort of magic. I've just called them magic bytes. Essentially, we didn't know what they were. I've done some research, I couldn't find anything. And before we can get a message to come from Free Cell Core to Codan, we need to have these magic bytes. If they're not set correctly, the radio never receives them. And this is really, really annoying. So the first thing I did was capture some like test data, and this was just sending pages from our Codan 9323 to various numbers, and just seeing what changes in those magic bytes. So you see the 2 columns here, M1 and M2, and you can see that even if you just change one number, it significantly changes. Well, yeah, are they really bytes? It's a good question. Also, given that we're talking about the protocol itself is 7 bits and 3 parity bits, so they're words. And anyway, they are definitely numbers. You are right, Mark. And we'll get into why Mark is probably saying that later. Spoilers. So, as you can see, changing one digit. Yes, words. Changing one digit changes, both the bytes, the words, significantly. But interestingly, you'll notice that I've only got to and from call sign there. If you change the message, nothing changes at all. So it's not protecting the message. It's not some sort of checksum for the message. It's not some sort of recovery thing. It was pretty quick to sort of realize that this is just to prevent interoperability, which is very much not cool. Very, very much not cool. So yeah, a little bit sad. I have done some research in the past about this. It took me a while to re-find this message because it's sort of buried in Google. Um, but Nova developer, same sort of problem. Want to build an app that can do these messages, and they can't work out how the page call messages. Those they've called them checksum. I don't think they're a checksum. Works. There's been a response back about someone who's tried to do it, and there's some blockchain cipher going on, possibly related to the private calling and that sort of stuff. But there's no answer. A lot of people have sent me this PDF. Please do not send me this PDF. I am so sick of this PDF. Every person I talk to is like, yeah, I know how to solve this. I know the protocol. I've seen it. I've got the docs. It's fine. And they send me this PDF. And it's always the same PDF. And this document is useless. The protocol is different. It doesn't have the checksum bytes in there at all. It doesn't explain how to calculate the checksum bytes. It's completely different. It's not related at all to what I'm trying to do. So please, do not send this document to me. It probably doesn't matter now. I know the bytes, so I'm not going to be asking for it. But it was hilarious just how many times I got sent this as the solution to my problem. But looking around at how other vendors do it, so you've got Skippy is a third-party solution similar to FreeCellCore, trying to implement this cell core and page call protocol on other radios. And it says it can send page calls, but then if you look at the fine print, you realize that it can send them, but the NGT and Barrett can't receive them. So that's not great. Then down the bottom we have a slide from Barrett presentation. And I've actually looked through a few of these slide decks, and I don't know the exact history, but I think sort of what happened is like Barrett was reverse engineering all these different cell core little bits and pieces. And in one presentation, they're like, we're working with legal to see what we can do. We've got most of it reverse engineered, next steps. And then this next presentation is like, oh, Codan and Barrett are working together. So they've got a deal going on there. Good for them. But like, I'm trying to work out, like, surely someone has figured this out, right? I'm not the first person. Maybe I am. I don't know. I'm pretty sure someone's worked this out. I feel like I can't be the first person. But there's definitely nothing online. The people that I have been able to gain access to, I thought would definitely know the secrets. Don't, and yeah, it's been quite challenging. So what can we do? I don't know. Find it weird calling myself a hacker, but I think I am. But the key point here is, like, our radio can generate it. It's sitting on my desk here at the moment because I've been doing tests. So I have something in my possession that can generate these magic bytes. The radio itself, the service manuals are online. It runs on an 8051 based chip, which is not surprising for something designed in 1993. It's what you'd expect. So it can't be that hard, right? It can't be super hard crypto. Ooh, is my audio too high? I can turn it down a little bit. All right. Let's see. Is that better? So how hard could it be? It's only 2 bytes. And the firmware's pretty small. The newer versions are 256. Ours that I have on my desk here is 128. And yeah, the service manuals are everywhere, so you can grab those on. Look at all the different components that make up the system. Um, yeah, so can we do this? Is it possible? I On the face of it, I think so. But some constraints before we sort of start heading into this is our radio is a radio that we use every day. Maybe not every day, but every day on a trip. And it's a 100 watt radio, which means it's still a 100 watt radio, and they sell on eBay for about $400. And we like our radio; it's good, and it's a pretty nice radio. So we don't want to break it. We don't want to, you know, test custom firmware on it. We don't want to poke it with like tons of probes. We don't want to rip out the EEPROMs and accidentally destroy them. But luckily, the firmware, the ROMs, are available online if you search around. So that's what we did. Found some ROMs and got to work. But I kind of want to set some expectations here. This project, it's been a lot more than I expected. So I want to give a quick warning that if you go down one of these paths, one of these rabbit holes, it may take longer than you expect. You'll definitely learn things that you didn't want to learn, and you might not get anything out of this at all. But if it's a sort of hobby project that you're working on, it's probably fine. I don't know how people do this professionally. I'm guessing they time box everything to, bits of work, but definitely think about as you're progressing through this, is this still fun? If it stops becoming fun, just stop. It's definitely this project, even though it's been 7 months, I've put it away and picked it up on and off. It hasn't been something that, I've just kept on going at. It's something that I've picked up when I've wanted to. And probably more recently, I've done a lot more work, maybe in the last month, than I had done ever before. So, yeah, just something to keep in mind that it might not work out the way it did for me. Yeah. So how do microprocessors work? We've talked about HF radio, so how do microprocessors work? So the 8051, every microprocessor is a little bit different, but the 8051 has a place that you can have program memory, and then it will have a place for the RAM or external memory. Has what we call special function registers. So these are essentially memory locations where hardware things happen or special things happen. But yeah, the 8051 is sort of in the center. You have your program memory in an EEPROM, you have your RAM in a separate chip, or it can be internal to the CPU. And then your rest of the radio hangs off these special function registers. But internally, the 8051 just sort of treats them all as sort of memory locations. So the same sort of instructions for writing to some memory sort of applies to the same parts of the rest of the radio hardware. But how does the CPU work? So we're just doing a high level overview here, but we have some instructions. It's sort of like a recipe, right? You're just going down the recipe going, add 1 to x. If x is 1, jump to 3, that sort of stuff. You have an instruction and an operand. An instruction is what do you do, and the operand is sort of a parameter to that, so it might be jump F4. Yeah, a little bit more complicated than that, but that's sort of the basics. You've got your, on the left here, that's just the location in memory where that instruction and operand is stored. All the instructions are pretty well documented online. So if you're wondering what an instruction does. There's plenty of documentation. You do have to be careful because some 8051 variants have slightly tweaked what some operations do. Generally speaking, it's all the same. Usually it's just how memory is managed. The program executes by incrementing what's called a program counter, and it's just tracking where it's up to in the code. So as stuff progresses, that program counter will increase, and if you get certain instructions that are sort of, jump if, then the program counter will jump to a different sort of location. It will change that program counter a different amount based on the result of that. And so that program counter is what's telling us where we are in the program. Now, all of this is just far too hard to comprehend in your head if you're looking at bytes like this. It's ridiculous. I'm not going to be able to tell you what 314D does. There will be someone in watching this that knows, but I don't. So we could use some tools to help us with this. I've been using Ghidra. It's free and open source, and it has 8051 support. And it lets you take those bytes from the ROM that we downloaded and decompile them, like disassemble them, so that we can get assembly out of them. We can see what instruction is running at that time. So you can just pick a memory location and press the letter D on your keyboard in Ghidra, and it will decompile it. So that's what you can see here in the two screenshots. Is I've just pressed the letter D, and it's turned those random bytes there that I had no idea what they did into something that I can now nearly read. So if you know assembly, or you learn assembly like I've had to do, you'll start seeing, what's happening when the code runs here. But we can do better. This is only the start. Ghidra also does a C-like output. It's not perfect, and it gets tons of things wrong, especially in 8051 land. But you can also help it by doing things like renaming variables and setting the correct data type. And what's happening is, as you're reverse engineering this, you're getting a better and better picture of what the code is doing. You're setting the data types to, good representations of what they likely were before the code got compiled. You're setting variable names so that you can keep track of, this is what this is doing. It's all getting a little bit better and easier to read, and you're getting a better idea of what the code is doing. And the more things that you have named and labeled, the easier it is to work out what the other things are. Eventually you'll find that you've labeled all the functions, so the one that you're looking for must be the one that's left, right? Hopefully you'll get there before you have to do the entire code, but eventually you'll get there. It's just sort of a matter of time. It's hard to know where to start decompiling though sometimes, or start investigating things. So in terms of decompiling, 8051, I think the very first address, like all zeros, I think might be the start for most. I don't know, look at the data sheet. But the other place is interrupt vectors are a good place, because you actually get an idea of, well, I guess to start with, what is an interrupt vector? So as your CPU is running, you might have something like the radio receives something, or the user pushes a button. When that happens, you want the CPU to react instantly. So we have these things called interrupts that basically tell the CPU, hey, stop what you're doing, do this instead, so that we can handle the user input or the radio input, and then go back to what you're doing. So these vector addresses are places in the code, predetermined places in the code, that will execute when those happen. And if you have a look at those, you get an idea of what interrupts are actually used. They're always in the same place for your specific CPU, so you can quickly see what pieces of hardware is timer 0 used, is the UART used, is I2C used. It's a place to look. The other place to look, less so for decompiling, but getting an idea of what stuff is doing, is strings. So if the program is printing out something like an error message, you can get an idea of what that function does based on the string. So strings can be a good way of working as well. We have a problem though. We looked at our datasheet, and the CPU said that it's an 8051 and it can do 64K of program memory. But the ROM that we downloaded is 128K. It looks like it has program there. Something weird is up here. What's going on? And what we have is a sneaky little trick called bank switching. What we do is we connect one of the input-output pins between the CPU and the program ROM. And this gives us a way of switching the ROM in and out between what we call banks of memory, and we can double the amount of program memory. This is quite tricky, fun and sneaky. But yeah, we get twice the amount of program memory that we would have otherwise had at the cost of one I/O pin. But the CPU doesn't really natively support this at all. It doesn't really know what's going on. So everyone implements this a little bit differently, so you have to be careful. I can't give you a general solution to this. Sort of what's going on is, a function is running, it needs to run a different function, it's in a different bank, so the code has to basically save its return location, change the extra address pin that we have. The entire memory gets swapped out, so now the CPU is looking at a completely different, memory, bank of memory, and then that function can finish, and then it can, switch the pin back, jump back to the return location. It's all a bit crazy just to get a little bit of extra memory. So that's what's happening here, is that we got ROM bank switching. And it's a pain. It is an absolute pain, because your decompiler doesn't really know what's going on. So you have jumps that are going to places in that aren't actually functions. It's all a mess. So what about emulating? If reverse engineering through Ghidra is hard, can we just emulate the CPU? There's tons of 8051 emulators out there. There's commercial ones, there's ones for education, lots of open source ones, lots of little hobby things. But it's actually not the emulator that's, the whole story. It's all the hardware in the, in the radio. So I2C is a protocol for talking to chips. You can talk to lots of different bits and of hardware through I2C. The advantage is it takes up 2 pins, and most CPUs have some sort of hardware I2C interface. The 9323 has several I2C interfaces, so one of them is in hardware with the CPU, and then the other ones are implemented through bit banging the GPIOs. There's other hardware like displays, radio controls. The bank switching itself is something that you need to implement. The emulators don't have an idea of bank switching like this. There's the UART and serial port. Each 8051 is implemented a little bit differently. So there's a Philips 8051 in this chip, in this radio. And yeah, it has slightly different configuration. So you have to think about all of this and, work with it when you're reverse engineering and emulating it. And I was talking about I squared c. One of the things that caught me off guard is like this function, it does nothing. It does nothing, 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 and then return. If I was decompiling an application, like a Windows application or a Linux application, if I saw this, I'd go, my decompiler is wrong, something is up, I'm decompiling the wrong thing. But this is legitimate code that gets used everywhere in the Codan 9323 because it's implementing I squared c, which needs a little bit of a wait in hardware. So you have to be careful if you've come from a reverse engineering software on computers to hardware that things are a little bit different sometimes, and you have to sort of go with it. You'll start collecting data sheets, regardless of reverse engineering or emulating. You'll start collecting all the data sheets for all the chips on the board because you need to know what does this pin do, what happens when this happens, how do I emulate this piece of hardware. So I think I had about 10 different data sheets for different chips for the part that I was working on, and switching between all the data sheets when I was working through everything. I kind of wish I printed them out at the start. It might be something you want to consider. I implemented just enough I squared c to make chips happy, so mostly just acknowledging that, hey, I've received something, or if they requested data, I'd send back all zeros. That worked for most things. The thing I did implement entirely was the I squared c EPROMs, just because weird things were happening when I didn't have that implemented correctly. So I did, as I mentioned, I did start emulating things. So I used Pi 8051, which is a wrapper for EMU 8051, both open source projects. Working in Python was really good. I could work really, really quickly in it. And I could also use the VS Code debugger and all the tooling that I'm sort of used to. This code is horrible, by the way. This is terrible. But I guess the point here is it can be terrible. I wanted to solve a specific problem, so I just did the bare minimum to keep on moving forward. There's no way I'd ship something like this into production. There's no way I'd give this to someone else. It's not expandable. It's not maintainable. It's just barely enough to get to the next step. Unexpected things will happen if you do something slightly different with this. So, but it did allow me to get to the next step, and that's the important thing. So Pi 8051 has callbacks for all your memory reads and writes and SFRs. And being an emulator, you're emulating the CPU. So you can start to do things like lie to the program. The program might write some memory, some external memory, to say, hey, I'm not transmitting right now. And you can just say, no, you are transmitting. That memory that you just wrote to say you're not transmitting, I'm just going to ignore that. You're always transmitting. And that can be really useful to put the program into a state that you want so that you can, run a specific function or test a specific function. So that's where this comes together, is that the emulator and the reverse engineering, the Ghidra stuff, all sort of fits together into this coexistence where you're using the emulator to see what the code you're reverse engineering does, but you're also using the code that you're reverse engineering to fix your emulator. So I had a whole bunch of different bugs, CPU bugs, my bugs, all of these little bugs in the emulator that prevent it from booting or prevent it from doing something. And so I'd use the reverse engineering to figure that out. But then I'd use the emulator to figure out what was happening in the code, because it's sort of hard to read tons and tons of assembly or tons and tons of decompiled C code and understand what it's doing. So bringing them together and using them together was super, super helpful. And I don't think I'd get to where I am today and being able to release this stuff without doing that approach. I definitely know there's people out there that will be able to just look at this 8051 code and go, that's the answer. But this is how I had to work, especially because this is not something I do every day. This is not my day job in the slightest. So eventually I got to a point where I could see stuff being written to where the display was meant to be. And this is super exciting for me. I got to the point where it was talking to hardware. It was booting up far enough that it was trying to do things. And the first thing I did is I wrote this display driver so I could see what it was doing. The first version was in like ASCII using Braille characters. Eventually went to Pygame. But I could see these screens, and by jumping to certain parts in the program code, I could get different screens to come up, and that helped me document some more functions. Yeah, it was super exciting. I'm going to pause for a second and have a drink. You should drink some water as well. Have you all hydrated? I hope so. Alright, so what's up next? Well, the emulator wasn't the only tool I built. Ended up building a CLI for the emulator, so it wasn't just printing lines of code. I could start interacting with it. I could set breakpoints, so I could stop the program execution at a certain point, tinker a little bit, and then start running again. Logging a lot of the hardware accesses was useful. That way I could get an idea of what the radio was trying to do. And started experimenting with things like the serial port server so that I could connect to the programming software. Another thing I built was this log output tool that would take my emulator log and color Ghidra. So it would be able to show what code is executed in the Ghidra view. And that helped me not get sidetracked on the wrong things. Droppy made a Ghidra script that helped with the bank switching, so I could see, so that I could click on the functions in Ghidra and get the right bank of memory. Super handy. What were we doing again? All right, Pagecall. Back to Pagecall. We got distracted with displaying things and emulating an entire radio. Should focus on the task that we set out to do, right? So our radio has a head unit and a base unit. Not all 9323s are like that. You can get it so that it's built in. But effectively, it's the head unit is just mounted inside the base. And yeah. But I still hadn't worked out if I had to find the magic bytes in the head unit or the base unit. I hadn't figured that out because all this time I'd been working on the base unit, and when I got stuck with the base unit, I'd start working on the front unit, and when I got stuck on that, I just flip-flop backwards and forwards. Not quite like figuring out what side had the magic in it. So eventually I got to a point where I wasn't making much progress on either, and eventually it kind of felt like I'd have to connect my two emulators together if I wanted to progress any further, and that seemed like a lot of effort. So I thought, you know what, let's try and get a hint. I tried to hold off doing this as long as possible, but I figured out there was a fairly trivial and safe way that I could tap into the communication between the front head unit and the base unit. This picture isn't actually showing it. This is me doing some extra work and tapping into the bit banged, what they call main I2C bus. But it's actually that white connector towards the front right that has the the connection between the front and the back exposed. So can we gather some hints from the communication between these two? And the answer is definitely. So use one of those SA Logic clone things. I'm not sure how expensive they are. I got one ages ago when I was much poorer, so surely they've come down in price as well. But it let me capture the communication that was happening between the head unit and the base unit. And I used a tool called PulseView, and it has a built-in I2C decoder, which is super handy. And I could quickly identify that the communication between the two did not contain magic bytes. So that means the magic must be happening in the base unit, with just halved the number of kilobytes that we have to search through to find our magic. But it also means that we have an idea of what the head unit sends to the base unit. And with that knowledge, we can send that to our virtual base unit. That's exactly what I did here. I replayed the page call message that I did on the real radio to my emulator, and it actually tried to transmit the page. I was surprised. I could see in my logs it was trying to trigger the tone generator, which I hadn't implemented yet, but it actually saved out the bit stream into the virtual RAM. And I dumped out the virtual RAM, and I could see it in there, and it included the magic bytes. This was like a really big turning point for the project, because it went from this is sort of unbounded, I'm not sure if I'll be able to do this, to I can now generate a log file for what happens. And I can just step through it, and it's just a matter of going through the steps to work out what happens. So this is a big turning point for the project. But I've only shown you what's, the happy parts in this project so far. I've spent days debugging CPU emulation bugs. I've spent days trying to understand what each I2C address is for, along with days emulating each one. Spent days emulating interrupt handling because the Philips chip has some extra timers on it. And I've spent days reverse engineering functions that aren't related. I maybe spent 4 hours reverse engineering 16-bit long division because I thought it was a crypto function. Nope, it was just dividing two numbers. Now it's like 4 hours. But we have a log now of every instruction that has happened when we perform an emulated page call. So we can line that up with Ghidra, and we can just step through it even just ourselves to work out what's happening. And over time, you start to build up a picture of what the code is doing and what it's trying to do. And you can set those variables and data types, and you can narrow down the specific functions that are important to doing those magic bytes. And then you can start turning those into Python functions. They'll be really rough to start with, but then if you look at them long enough, they start to simplify, and you can make generalized versions of them. And at that point, I also wrote test cases for the page calls that I already knew about, so that I could test if I'm generating the correct magic. I ended up adding to those tests because I found some edge cases when testing with real hardware. But I think we've got it. So this is the magic. I don't really know what to say at this point because it's not exciting at all. It feels like it should be exciting, but it's just like we have some key data, we do some XORs and additions and swaps. It's, it's not hard, but it's just finding it and working out what the inputs and outputs are. These are functions, or what's been like rewritten here. The assembly code for this is stuff that I've tagged 6 months ago as this is probably it. Like 6 months ago, I knew that this would be related to the page call. But the thing is, I didn't know the inputs and outputs. I didn't know how they were called, in what order, with what data. that all sort of stuff. I didn't even know that it turns out that they pack these as BCD digits at the end of the day. So there's some weird sort of packing logic that happens because they have to be 0 to 9, otherwise it won't fit. Um, so it's a bit frustrating to know that you found it 6 months ago, but it's not like you could do anything at that point, or at least I couldn't. But yeah, this is the magic. It's on GitHub, the whole thing. There's nothing too special about it. That's just the algorithm it uses. Thanks to 6P4C and Alex for helping with like making a generalized form. Super useful. But yeah, this is it. So we have a Python implementation of the magic for pages. These are the test cases I was talking about, so I just collected them. These are all taken from RF, so not using the emulator, not using the Python code. These are recorded by using the radio to sort of transmit them or receive them, so they're confirmed, good input output. And so yeah, if we refactor anything in that code, we can run the tests and see if we've messed something up. Because very slight changes will still output numbers, but they need to be the right numbers. So this means that FreeCellCore now has pages. You should be able to download it today. I'm not sure if GitHub Actions has finished building a Docker container for it, but in PyPy there should be pre-built ARM binaries for it. x86, you're going to have to figure that out yourself, but you should be able to build it from the source code. Web design is definitely my passion. I don't know why the page button is all the way up there. I don't know. I don't care, to be honest. I can send a page. That's the important thing. But yeah, so yeah, here's some clips of my Codan 9323 and Geordie's Codan 9323 receiving a page that was sent by FreeCellCore. It receives it just like any other page from any other Codan radio. You don't have to configure the radio in any specific way, apart from leaving the privacy setting turned off. It will receive it just fine. Yeah, it works. The fun thing was I had never received a page on our 9323 before, so I had to look up the user manual to figure out how to open up the page message, like to actually see the message. And it felt so weird to me that I know the insides and outsides of this entire radio from a hardware and firmware side of things, but I didn't know how to operate the menu to open up the message because I've never had to do it before. But yeah, so questions, ask your questions in the chat. I'll try and answer them or send me an email. But here's some ones that I thought might get asked. No, the emulator is not going to be released. It's not useful to you. It's barely useful for me. It's terrible in so many ways. To package it up and put it in GitHub, it's just not worth it. The Ghidra project, it will contain too much sensitive data to share suitably. There'll be copyright issues if asked to do that, so no, not happening. 6-digit cell core or GPS tel core privacy key. These things that could be implemented, I am not going to because they're not useful to me. If you figure out how to do them, submit a PR, I'll have a look. Testing it can be hard because I need to configure the radio and do all that. Maybe something I might work on is the unlock codes. So the Codan 9323 has a way of unlocking features or resetting the key lock. If you ring up Codan and provide them a code, I don't even know if you can ring up Codan and ask about these old radios and get unlock codes anymore. So it might be useful to have a way of doing that that's public. But yeah, I'm not seeing any questions in the stream, so maybe I covered everything well. I don't know. Um, or haven't got there yet. But yeah, either way, here are some links. So I've done a talk on overlanding and radio that some people might find useful. That was at Internetpalooza. Link to the Free Cell Core project is there, and there should be a blog post up, the part 2 for Codan Cell Core on my blog. Yeah, that is it. Thank you all for listening. You've been lovely, lovely people. I'm just going to double check to see if I haven't missed any questions. No, no, I think we're all good. Any final questions? No. Well then, thank you all for your time, and hopefully you got something out of this. At least indulged me in my 7-month project that I really didn't want to do. But it's done. I can move on. So thank you all, and have a lovely evening/morning.